Hello, hello. Here we are. Hey, Thomas, how are you doing?
Hey, Luca, pretty good. 5
Nice.
p.m. on Friday, almost weekend.
Yeah, yeah. Feels good. Feels good. Awesome. So thanks everyone for watching. I know, I meet people, they bring out the fact that they watch the stream. So that's good. We'll keep doing that regardless, but, uh, all right. So episode 4. So today we'll get into transforms and what it means to transform your program, and which is basically why this is all about, like why we're going through all this pain of acquiring the program and so on. So let's take a step back. Let me share my usual scribbling pad here. And yeah, so this was the last time, you remember, we went through the high level architecture, acquisition, execution, then we looked at Torch compile, again, acquisition, dynamo, execution, inductor, and JOX. And we showed 3 different programs and how they transformed themselves and what the intermediate representation, what the internal representation for those programs were. And now we're getting into, now that we have a representation of the program, then we can think about automating the transformation of that. Because if you transform a Python program directly, it's a lot of work. You have AST or whatever, it's really complicated. But if you have a sequential representation of your program, then it's made by like simple statements, like do this, do that, do that. Then you can start reasoning about all the statements and how to rearrange them, insert new ones, replace those who are there that are there with others, and so on. Awesome. So I want to touch base a bit on this theme to talk about like thick and thin frameworks. So you might have heard about Llama CPP, or which is this library that you can use, or like executable that you can use to run Llama or other models, Mistral and so on consumer hardware, like a CPU or a GPU, or consumer GPU, really, really fast. And also LLMC that Andrei Karpathy created on the training side, and you can train things really fast. Faster maybe than PyTorch implementation. And I'm arguing that the reason why these things are fast is not because they are in C necessarily, right? But what is it that makes them go fast is the fact that they're very thin abstraction or zero abstraction or as minimal as possible abstraction on the kernels, on the way you make trade-offs. So in this program, in a program like Llama, yeah, go ahead.
And obviously, because like they are fast, because lots of people looked at it and everyone made them a lot faster, a bit faster, right? It
Exactly.
starts by the heroes doing their thing, but then there's lots of people like looking at what can be made faster. So there's a lot of work, a lot of sweat that makes these
Absolutely
fast.
Yeah, if you go on the repository, you can see how much passionate work and labor of love has gone into making things fast. But I'm arguing that wouldn't have been possible if something was made out of different layers in different libraries, right? The fact that you can concentrate the front end as harsh as it would be, because it's C, is low level code, people are not used to it. It's not rocket science, but you need to, it's a bit less convenient than calling into Python code. But then you can optimize things so in such a granular way, going all the way from your C front end to the CUDA kernels, going through how you load things into memory, and you have control on super fine control of all these things, so that few people that devote time, or a few people, a bunch of people that look at that can look at the whole thing back to front and front to back, and find optimization front to back again back to front, and that is what makes these things fast. It's not the fact that they're in C, it's the fact that they can represent everything in a very short stack. And in a way, that's what we are striving for in Thunder, but without making the compromise to write your code in C or to go too low level. We want to get to a point where we take a PyTorch program or a program expressed as you would express it in math and get to the same level of control so that you can optimize everything of that program without, your call going back into something and be lost. And at that point, you lose the ability to really optimize that thing.
Right. We find
Awesome.
the kernel.
So, yeah, you can operate at the kernel level, but maybe the kernel is not what makes you go fast. Today, we will see that sometimes it's reducing the memory pressure what makes you go fast, and the kernel is just something that runs as fast as possible. But if moving data back and forth is slower than the kernel, you can spend all your life on that kernel, but the thing will not go fast, right? And this is one aspect of why we want transformations, because once you acquire a program and then you put it in the IR that we have, in the intermediate representation, and we make it something that we can manipulate and transform, that's the low level representation that we have. Like, that's where we can actually go from the top, which is our trace, to the bottom, which are our kernels or primitive operations, and we have full control there. And the other advantage of having a transform is the n-by-n problem. Do you want to talk about that a bit?
Yeah, so obviously, I mean, if we take this week, like, there was Llama 3.1 released, Mistral also released their new models. So there's really has been a lot going on. And so now you have that many models, and we could now go all and optimize them one by one. And add all the optimizations. You need the cool flash attention. Well, probably if they release Source, they already have it because it's really not well without it. But then you have the KV cache, you have the map molds where you might have your secret sauce or figured it out for Llama 3, and now you need to move all this over. And so what happens is that you have like N models and M optimizations that applies to all of them, but you can't just copy the code because it's like too much work. And then it would be cool to like separately describe them, because then instead of having N times M optimizations for each model, you have N models and M optimizations, and this only adds instead of multiplies. And so this is the hope. And in some ways, one of the things we say here is that we want to separate the what, like what model, what computation, from the how to make it fast. And this separation really is what enables us to go there, because there's like an entire llama herd there.
Exactly.
And a zoo of optimizations. And so you can't have a zoo for every llama.
Exactly. So that's exactly the point. So we will now go into what a transform is and try to understand, once we acquire the program, we saw it multiple times now, how can you write a transform for it? What is even a transform? How can you code it up? Is it something you do manually? Is it Python code? And what steps do you have to go through to be able to implement one? And usually we think about compilers with fusion passes as very complicated things. They're not super simple, but they're not like super hard either if you put more, enough time into it. And I would say that the goal for Thunder is to make transforming programs as a first-class citizen, so that people can start shipping transforms. I can give you my transform. You can give another person another transform to apply on their model, and so on. We'll get into composition in the future. But one thing that we want out of transform generally is optimizations. So optimization can be, I run the model faster and I distribute it and so on. So today we'll see an optimization, which is quantization, that enables you to have fewer bits to work with. And we touched briefly upon it, but let's rehash this concept again so we know what we're looking at. And then in 2 minutes, we get into code. Right. So you have a model, and the model will have a lot of weights. And these weights can be, many layers, many weights, these tensors full of numbers. And these numbers are usually represented either in 32 bits or in, sorry, the pen changed under me, or bfloat 16, which is like 16 bits. So if you have a million numbers in 32 bits, you have 32 million bits. If you have a bfloat 16 representation, it uses fewer bits to represent the same number, and you'll have fewer of them representable, but it's more than enough. So bfloat 16 usually it's a good thing to adopt because it's seldom associated with a lack of convergence or lack of loss of quality during inference, and it uses half the size. But of course, you can even go down further. There are many quantization techniques. But why do you want to quantize? Well, because as we said multiple times, if you have your main memory on a GPU, and you have your tensor core, whenever you do a computation here, you need to put the results back. And then if you do that multiple times for multiple operations, sure, you confuse your things, but once you fuse your kernels, once you have fused all your computations in one big kernel, but you need to call this kernel repeatedly. So in the best possible situation where you fuse everything, you still need to say, okay, now, do this forward, then generate the next token, generate the next token, generate the next token. And as you do that, you cannot just enqueue all the kernels one after the other. You still need to put some stuff back and load them, right? Or, as you go block by block, it depends on how your fusion is structured, right? And typically, this time here will depend on how many bits you need to shuffle. And cards have a limited bandwidth. So what is bandwidth? Bandwidth is measured in gigabytes per second. For example, a A10 GPU will have 600 gigabytes per second. So if you exceed that, you will take multiple seconds to even just store a result of a computation. L4 GPU will have 300, nominal, of course. And this will really dictate the speed at which you can go. So what you can do, since you have a fixed bandwidth, to minimize this time, where you can decrease the numerical precision here, say to 4-bit, and in this case, it will take a fourth of the time, given the fact that the bandwidth is fixed, to transfer this. And you see that for large enough models, for weights or even for the KV cache, this time really dominates, especially if you just serve one request. So today we will learn how to take a model and turn its weights into 4-bit using a transformation so that we can make the computation faster, as well as fuse the kernels that are in it all together in a single pass.
Right. And so shall we jump into the code?
Of course, I just gave you access to power.
So let me share my screen here. And so I'm going to start like our notebook as always. And I was going to, on the Lightning Studios, and I was going to show you like the work that we did this week, optimizing a model, Llama 3 in this case, to get really, really good performance. But unfortunately, I managed to crash the program at the last minute. But so we will probably show next week, and then it'll be very, very smooth, right?
Yeah, this is live. This is live.
Yeah, that's
So
what happens when
you can fix it. Yeah, yeah.
live.
Okay. But let's say we'll lay down the foundations
Yeah.
this week, and we'll show the full thing next week.
So let's not do Llama 3 right now, but let's do just a small example, an MLP, where we can see really good what's going on. And so obviously we need Torch and Thunder. And let's have an MLP, and for convenience, I will just initialize it directly on the device. So we put it on the GPU. Oops. And so what do we want? We want an MLP that's a model with a number of layers, and I can use the sequential class here. And then we have a linear layer, say 512, 2024. Then we have an activation function, and the modern one is this one. And then we have linear layer again, and this goes back to 512, say. And because we're talking about inference in this, because we don't want to train Llama 3 today, but we want to make inference fast. So, and the quantization is particularly relevant there. So I will do requires graph false here. And if you had something in there that has a training eval mode, you would put it in the eval mode. But so we have this, and we of course we need some sample input, and I'm not very creative, so all my sample inputs will be random numbers. And let's say we have a batch size of 1 and 512 features to feed into. So this is our model, and it's not very fancy, right? We can now call MLP imp, and this will give us some output large enough. I should have made this smaller, right? So let's make this two thing. So here. But now we can compile the model, and we saw that like last time we can call thunder compile of the model.
Compile?
Sorry. I'm very old. Thunder JIT of the model. Sorry. And so this gives us a model to call with our input again, and it will produce the same output. But now, of course, we wanted quantization. And so quantization can be viewed either as something that is part of the model that you stick into the model, or it can be viewed as an optimization, as we do today. And so what we do here is we import from Thunder the quantization transforms, and we take today the bits and bytes. Will it have tab completion? No. Bits and bytes, linear quant form.
Yeah, Bits and Bytes is this library by Tim Detmer, and he did a lot of work first on int8 quantization, and then he went into 4-bit quantization for floating points. And it was basically presented at the NeurIPS competition he talked about it. And when he was talking about it at the New York competition on the efficient LLMs, he came up with saying, "Oh, I'm getting into CUDA mode," and that expression was what was inspired Mark Serafin to then start the CUDA mode Discord channel, and I was there, so it was nice. Okay,
Right.
I'm giving you time to type things.
Yeah, right.
Correct.
Like cope with my error messages. Let's get the bits and bytes executor. This will give us this, but we also have this transform, and I cheated, and it's not called a transform, but we can apply this transform just by passing a transforms parameter here. So bits and bytes linear transform, and this is all we need. But then we need the executor, the bits and bytes executor too. So here we go. And if we now look at this model, I should make this nicer, right? We can format it so everyone can see what has happened even after the fact. And so now this gives me a quantized JITted model, and if I run it, I can see that the values are slightly different, right? If I compare it here with the original inputs, they're slightly different from the quantization, but they're very close. And so this is what the quantization does. And in the small example, we don't see the huge time savings, but we can use the same trick as last time to see what's going on under the hood. So what has happened here is that the transform, the bits and bytes linear quant for bit, did like 3 things. It quantized the weights. It then changed so it would get all the amended quantized weights to the computation, and then in the computation it replaced the usual matrix multiplication or linear layer with the quantized one. And
just to clarify, what happened is not that we go into the NN module and monkey patch it, right?
No.
Just to reiterate, and I think the viewers will already know this, but we acquire the program and then each op, and we can actually see it now, will be treated differently. Yeah.
Yeah, so if we see the model, it will still be the same thing. And we could still run it from there too, and it would work. So if I absolutely had to, I could do this. So it's still the original model. But so what has happened, we can again see with the last traces, which gives us the new the result of the transformation step by step. So if I look here at Thunder last traces of our model, and we take the last one, that's the one that's actually run, we see that, well, yeah, here there's, unsurprisingly, these are here, but then there's also like new ones, absolute maximum and code tensors, which have been inserted for the quantization. And then we see that the linear layer now actually uses a BNB matmul, which is a new symbol that our executor provides. And so we feed in the required parameters here and have that replaced, right?
Yeah, one of the interesting things that we see here is that the computation actually has more arguments now. Like as you, maybe we covered it briefly, computation is broken down into 3 moments. One is the prologue that goes from object-oriented to functional. And then we have the computation trace, which is purely functional. So everything that happens needs to be in the arguments. Otherwise, it's kind of insulated from the outer world. And then the epilogue that goes back into object land and non-functional land. So here, basically, we see that the computation has been enriched with 2 arguments that are arguments that come from the need of quantizing. And if you think about it, 4-bit, it's a very small amount of possibilities, right? And so with 4-bit, you can just represent a handful of numbers. But in order to represent enough numbers for the computation to happen, then you need to equip it with kind of scaling factors so that you will get the numbers in the correct range, more or less.
Yeah. So what this does is that the AppsMax is the scaling number, actually, like the largest magnitude. And the code book, actually, we wouldn't have to pass that in here because it's fixed. But so if we go jm get parameter, and we can just, I could just copy it here, right? So this code book will go from -1 to 1, and these are always the same numbers. And this is from an empirical study that is in the Q-LoRa paper. They give these numbers and motivate them. But so what happens is that we have these two additional tensors that the quantization wants to see, and so we provide it to them. And so we have it here as parameters. We could also use buffers, so the Prolog gets these off the Thunder module because they're present on the Thunder module, but not actually on the module. Which also means that if you want to load a snapshot of your model, you need to do the quantization again on the fly. And so the transformation will take care of all of these bits. It will transform the model, it will transform snapshots if you wanted to, and it will transform the Prolog and the compute trace and the epilogue if you want to.
Yeah, so it's a bit more than just replacing a layer with another layer. It's replacing the layers with modules with another, like linear with its own implementation of linear or functional linear, but also enriching the computation with extra inputs. And this is already a bit less than trivial to do. And then, of course, if you use bits and bytes vanilla, then this thing will happen by patching stuff around the Python module. The big difference between these two approaches, like monkey patching and going through this transformation, boils down to, will I be able to then take this and do something else with it that is composition between transformations, as opposed to I monkey patch my stuff and now if I touch it again, it kind of breaks.
Yeah, for example, last time we were very excited that we had NVFuser fuse these things, the Gello operations, and now that is gone. But this is gone because we stopped NVFuser or the executor to do its thing. So if we do here Thunder get default executors,
there's a missing D.
Oh yeah. By probably in the Thunder session 2000, we will have no typos in Thunder anymore. So if I run this with a fuser or with the default executors, and NVFuser is one of them, you see that we get our fusion back. And so this is like the n times m problem. I want to optimize the mud molds using quantization, but I also want to optimize all the other bits with whatever I had before. And so this system lets us do this, and it does so by going step by step. First it does the quantization, then it might do distributed, and then it might do something else. And what's more, you could even, if you have a model that doesn't fit on your GPU, you could do the quantization before actually materializing the model on the GPU. So that's like a very nifty thing that you can do, because you can here have a list of transformations where we have only this one, but you could have an entire series, and then you also can have executors that optimize all of your model.
Yeah. And I think that you touched upon two very important points that I want to stress before we part ways. One is you mentioned distributed, because distributing computations can happen by inserting collective calls, like saying, oh, now I want this tensor to aggregate, to be the average or the sum or whatever of all tensors on all machines. So please, gather all the numbers for me and present the result of this operation. Or I may want to do other things that deal with sending stuff and receiving stuff anyway, or waiting for stuff. And this can be inserted in the computation trace as a transformation as well. So now we have a very tidy way to say, okay, what if I want to compose quantization with FSTP? You need to implement FSTP as a transformation, which we do in Thunder, and then you can compose the two things together. And that's very interesting.
So we could like, it's yeah. So this won't work, but so essentially this would be the gist of it. But I only have one view today. Maybe we'll show it another day with the file distributed here.
And then the other interesting thing you said is we can do all these manipulations without basically ever allocating any tensor. So because all the acquisition we do relies on meta information on the tensor. And then we'll probably get into data-dependent operations at a later stage when we get advanced. But essentially, everything you're seeing here doesn't rely on the values that the tensor have, only on the shape of the tensor, the type of the tensor, and so on. And so the really cool thing here is that we can do all this symbolic manipulation. I could do it on my laptop, and my laptop doesn't even have a GPU. And then I can basically, quote, send the result for execution on a device. And that's kind of game-changing, because I can reason and manipulate a Llama 3 for 100 billion symbolically before, and do all the quantization, distribution, and reason about it until it's time to run. And at that point, I need the memory, but maybe transformations have reduced the numerical precision or reduced the width of tensors because now I'm doing tensor parallelism and so on. Anyway, we had some question about why Thunder, and I think this episode kind of made it as clear as possible and why we're so excited in this journey that we have embarked ourselves in. And yeah, I hope, next week for sure, we'll show you some mind-boggling numbers coming out of the operations that we are doing here, which is quantization, and what it means when you run a fairly large model on a consumer device with limited bandwidth, and how much difference it makes. And yeah, we made it through the 4th episode, apparently. So thanks a lot, Thomas.
Yeah, thanks, Luca. And you have a good weekend. And of course, everyone joining us on YouTube too.
Post questions.
And then we'll see next week.
Yeah, next week. Yeah, they do this, post questions under. Okay, great. Bye. Thank you.